Finally, I'd like to talk about X-ray detectors. This is what we measure X-rays with. We have two types of detectors. We have this detector that's traditionally fitted to a scanning electron microscope, and it's the energy dispersive X-ray spectrometer, which is EDS or EDX, whichever one you want. It's quick and easy to use, it's solid state, it's cooled. In the old days it was cooled with liquid nitrogen, now they're Peltier cooled. They have some spectral artefacts I'll talk about later, called sum peaks and escape peaks. And you don't need to know what elements are present in your unknown material. You basically put it in there, and whatever X-rays hit the detector are measured. Its spectral resolution, full width half maximum, is about 125 eV, but the detection limits is somewhere about 0.1 weight%. And for standardless quant, I'd say its accuracy is about roughly 5% relative. We've already talked about that. Sometimes I can get down to 2%, and other times I'm hundreds of percent. The other type of detector is fitted to a microprobe, EPMA, electron probe microanalyzer, and it's called a wavelength dispersive X-ray spectrometer, WDS. Theoretically, you could also say WDX, but no one says that. The probe has multiple WDS spectrometers on it. It also has an EDS spectrometer on it. The real big difference between the SEM and the probe, I actually think, is how you use it. You have different detectors and they help, but in reality, with most people on the SEM, certainly in this lab, we're looking for throughput. We're using the factory calibration standards, standardless quant, semi-quant. Very quick, you're going in 10 minutes. With the WS detector I'm calibrating that today on my known reference standards. I might spend at least half a day doing that, maybe even longer, but it allows me to give very accurate analysis. So to me, what makes probe excellent is the workflow. However, the WS detectors they're slow, they only measure one element at the time. Because you only measure one element at the time, you need to know what you're looking for, otherwise it takes too long. There's very little artifact, spectral artifact, but you can get higher order diffraction peaks. I'll talk about that later. They got much better resolution. Full width half maximum, crystal dependent here, but we're looking at about 5 eV. Very tight X-ray lines. So overlaps, that lead sulfur overlap that was a problem with EDS is not a problem with WDS. Thermal noise is not an issue. Detection limits, routinely 0.01 weight%, and I can get better than that, okay? So that's 100 parts per million. Accuracy, 1 to 2% relative for majors. I can control that by running reference standards as calibration checks. But every time you find it's not good enough, you might spend hours fixing it up. It's not a quick day on the probe. In fact, some of my best analysis on the probes have been 3-day experimental runs. So that's the probe and that's the SEM and how I use them differently. I should point out that the EDS detector is cold, it's cooled. It's often the coldest thing in the chamber, and that can be a problem because if we let moisture into the chamber in humidity, ice can condense on the EDS detector. But also, if you put specimen into the chamber, the vacuum chamber, that has a solvent with it. That solvent would evaporate under the vacuum, but it would tend to condense on the coldest surface. That what doesn't get pumped away will condense on the coldest surface. That's my EDS detector. My EDS detector has a thin polymer window on it to let low energy X-rays in. If you use some not nice solvent and you don't properly dry it out before you go to the SEM, and remember cleanliness is important in the SEM, that solvent contaminates my detector. If that solvent is aggressive to a polymer, such as acetone, you eventually break my detector window. And I've seen that happen to multiple detector windows, people not taking care of them, not because they physically touched them, but because they never took care of the cleanness of their specimen, contaminating the detector window or actually breaking the detector window. It does happen. I'm going to quickly talk about how the detectors work. I've drawn a schematic up here of a EDS detector. It's a semiconductor. You've basically got silicon atoms, and each silicon atom is bonded to 4 neighbouring atoms. That's a standard solid state device. That bond between neighbouring silicon atoms is a shared electron. What can happen is an X-ray can come in and it can knock out that shared electron. So that bond between 2 silicon atoms, a line I've drawn up there, is replaced by an electron hole pair. The hole is the positive vacancy in the matrix, and the electron is the negative electron that was there and has now been knocked out of it. Once we've got electron hole pairs in a semiconductor, we can conduct electricity. The thing is, those electron hole pairs will naturally recombine, which doesn't help us much. So we've got to make sure they don't recombine. So with my silicon chip, I have a plate at the top and a plate at the bottom. The X-rays come in from the left. One of those plates will have a positive charge, the other one of those plates will have a negative charge. And what that does is the negative electron gets attracted to the positive plate, and the positive hole gets attracted to the negative plate. Of course, the hole moves by the electrons moving the opposite direction, but let's not worry too much about that detail. The main thing is, by having a bias on the plate, I separate those electron hole pairs. The X-ray enters and it uses up all its energy creating electron hole pairs. We know that it takes 3.8 eV of energy to create each one of those electron hole pairs in my detector. So when a calcium K alpha enters at 3.7 keV, that creates roughly 1,000 electron hole pairs. And we separate them by having a bias on the plate. In the end, I put a charge on 2 plates. In normal electrical terms, that's called a capacitor. I've charged up a capacitor. What do? I measure the voltage on that capacitor. The voltage correlates to the charge correlates to the X-ray energy. By measuring the voltage, I calculate the X-ray energy that caused all the electron hole pairs. Of course, I've only got about 1,000 electrons there in terms of absolute charge. That's a very, very weak charge. So that voltmeter is a very high quality voltmeter. It's a FET, a field effect transistor. It too is typically cooled so as to keep thermal noise to a minimum. That is how an X-ray is detected. The X-ray enters the chip, forms electron hole pairs which are kept separate. That forms a charge. By measuring the charge or the voltage, I know the energy of the incoming X-ray. Very simple and elegant device. We've got to do 2 things. Why the X-ray is forming electron hole pairs, we can't have any other X-rays come in. It destroys the quality of the measurement. And we've talked about that earlier. It's called the dead time. 2 X-rays come together, we got rid of both of them, reset the crystal to ground state, start again. So when the dead time is too high, 100%, too many X-rays. We adjust the spot size, the number of electrons, to get a dead time somewhere between 5 and 50%. We want well-spaced X-rays, 1 X-ray at a time. There's 2 other things that can happen, and they're shown down the bottom of that slide. First of all, if I get 2 X-rays that land too close together, I can pick up I've got 2 X-rays there. I've got 2 pulses, too close together, I reject both pulses. That's dead time. What can sometimes happen is 2 X-rays can land at exactly the same time. And my detector doesn't realise it's 2 X-rays because it doesn't see 2 pulses because they land simultaneously. For example, I get 2 calcium K alphas landing at 3.7. So rather than count them, which I should, as 2 3.7 keV X-rays, my detector counts them as 1 of 7.4 keV X-ray. It adds the energy together, and that's called a sum peak, a summation peak, an addition peak. You do see that in detectors where 2 X-rays land simultaneously, they produce another X-ray. Another good example of a sum peak is aluminium. Aluminium produces an X-ray, aluminium K alpha, 1.5 keV. 2 times 1.5 is 3 keV. 3 keV is the same energy as an argon K alpha X-ray. When you're looking at a high aluminium alloy, it's natural to get some peaks formed by 2 aluminium K alphas which will be a peak at 3. Argon, which is a Nobel gas, you do not have argon in solid solution in your aluminium alloy. That is a sun peak. Just ignore it. If you choose to label it argon and you hit the ZAF correction button, you will get a certain percentage of argon in your aluminium alloy, which if you know metallurgy makes no sense whatsoever. One of the biggest filters is, does this make sense with respect to my material? You don't have to always be an expert in analysis. Sometimes being an expert in the material is the only guide you need to make sensible decisions, make sensible material decisions. And now the other artifact is a silicon escape peak. We've already talked about fluorescence. That's when a high energy X-ray stimulates a low energy X-ray. Again, for example, calcium K-alpha, 3.7 keV is entering my detector. My detector is made of silicon. Silicon K-alpha, 1.7 keV. When my calcium enters, it may fluoresce a silicon X-ray. If that silicon X-ray goes deeper into the detector and forms electron hole pairs, that's not a problem. However, if it leaves the detector, I've lost that amount of energy from electron hole pairs. And so I count the wrong amount. So sometimes you get your primary peak minus the energy of a silicon K-alpha. In this example, 3.7 calcium minus 1.7 silicon produces a silicon escape peak of 2 keV. That is just the energy that has sometimes escapes the detector. And it looks very close to a zirconium or phosphorus peak. Again, you have to make that decision. We can talk more about it if you have problems interpreting spectra. I'm always happy to come in and sit beside you and talk to you about it. But the main thing is, I think most novices assume that every peak they see is real. Certainly, if you've done properly, the big peaks are real. And some of the little peaks are real too, but some of the little peaks could be summation peaks or escape peaks from the big peaks. That's something to bear in mind. Let's now talk about a WDS detector, a wavelength dispersive spectrometer, traditionally fitted to a microprobe. But I have fitted them to SEMs for various reasons. We have the Bragg diffraction law, n lambda equals 2d sine theta, where n is the order of diffraction, lambda is the wavelength of the X-ray, d is the d spacing between the atomic planes of the diffracting crystal, and theta is the angle that they come out at. Effectively, we all know that if you shine white light into a prism, we get a rainbow coming out of it. That rainbow is a diffraction effect. Each wavelength will come out at a different angle. And the same thing happens with my diffracting crystals. These are crystals mounted off to the side. All the X-rays from the specimen hit those diffracting crystals, and each different wavelength gets diffracted in a different direction via the Bragg diffraction law. And we know that basically chromium goes in at 1 theta, iron goes at a different theta or angle, and nickel will go at a different angle again. So rather than try and work out the energy of my X-rays, I just use the diffraction effect and I go to the position where I know this is where iron will appear. And I know via diffraction, I count these as iron X-rays. Then I move my detector to another position where chrome will appear, and these are my chromium X-rays. And so forth for all the elements in the periodic table. It's slow, you've got to do one element at a time, but you get very good spectral resolution. Why? Because if you recall, when you get waves, they can constructively or destructively interfere. When you're on the peak, they constructively interfere and you get a strong peak. As soon as you go off the peak, you get destructive interference, and you get a very flat background. So that's how the microprobe works. And because of that, you've got very high spectral resolution and low background, and that gives better accuracy, better detection limits. But it's one element at a time, and you've got to measure the backgrounds independently. I actually say to calibrate a WDS spectrometer, I need 30 minutes per element. As you begin to add elements to your analysis, it really adds up on the calibration. I've covered all the basic theory I want to cover, and I thank you all for listening to me, because I know it's hard to listen for such long periods of time. So before I go, I just want to show you a few worked examples, just so you can see what it really looks like in real life. So this is an EDS spectra of some stainless steel, and you can see I've got my iron peaks, my chrome peaks, manganese peaks, nickel peaks. On the right, these big peaks, around 5, 6, 7 keV, they are the chrome and iron K alpha. These ones down here are the chrome and iron L alpha peaks. You can see below 1 keV in energy, the spectrum becomes very crowded. This is the iron K alpha, this big one here, and this small one here is the iron K beta. This is the nickel K alpha, this is the nickel K beta. Here's an interesting fact. This is the chromium K alpha, and here is both the chromium K beta and manganese K alpha, if manganese exists. Do I label it? Do I put it into my analysis? If you look at the height of the K alpha to the K beta for the iron, and then you look at the height of the K alpha to the K beta for the chromium, this K beta peak, if it's the same K alpha to K beta ratio, which it roughly should be, they're very close transition metals, this chromium K beta peak is quite high given the height of the K alpha peak. So my interpretation is yes, there is manganese there, so I'm going to label it. You can also see a little bit of silicon there and a little bit of moly there. This is a spectra I acquired and I labelled. I then hit the quantitation button, and this is my answer in both weight percent and atomic percent. And you can see it changes. Silicon is 0.65 weight percent, but 1.28 atomic percent. It doesn't matter what you work in, you can convert, but don't get the two confused. Know what you're working in. And in particular, you can see I'm going to work in weight percent. I've got about 1.74 weight percent manganese there. And the software has corrected well, and I think that's a pretty good answer. If you look, this looks roughly like what I would call an 18-8 stainless steel. 18% chromium, 8% nickel. And I've also got a little bit of moly in there, so probably a marine grade stainless. Let's have a look at this. Look at how small that moly peak is. You can see it, but let's talk in terms of weight percent. That translates to 1.3% moly. And that silicon peak, you can see there, is about 0.6 weight percent. So you can see, as these numbers get smaller and smaller, concentrations, those peaks are going to be harder and harder to see. What's happened here? I've got my copper K alpha peak, I've got my copper K beta peak. Right here, about 1, which I should be able to see, there should be a very large copper L alpha peak. I don't see it. So what's happened there? We always tell you to leave the SEM under vacuum. And this is a person who finished using the SEM where the whole chamber vented. They were the last person on the machine, and then they went home and they left the SEM at air overnight. That hurts my vacuum system when I'm trying to pump down the next morning. Given the humidity, that cold EDS detector was exposed to moisture in the air and ice formed on top of the detector. Not enough that you could see it with your eye, but enough that the ice preferentially absorbs the low energy X-rays over the high energy X-rays. As soon as I saw that, I knew I had an ice detector. I then proceeded to warm up my detector and de-ice it. This is an old liquid nitrogen detector. That actually took a few days to gently do it. And then the same detector, a little bit later, de-iced, freshly de-iced. And you can now see the copper L peak is enormous compared to the K peak. If you ever end up buying an SEM with an EDS detector, one of the things I first do when I get it straight away is I just put a piece of copper in there. A piece of wire will do, and I grab a copper spectrum at 20 kV, and I just keep that, and then I reference it, and then every 6 months or every year I grab another copper K alpha spectrum. And you'll probably notice, depending on the SEM, depending on the detector, depending on whether you have an antechamber or not, but over time the L peak begins to decrease relative to the K peak. That's ice building up. And my general rule of thumb is, once the copper L peak is the same height as the copper K peak, I need to de-ice my detector. If I'm doing a lot of light element work, boron, carbon, nitrogen, then I'll de-ice it a lot more sooner than that. It's the low energy X-rays that are most heavily absorbed by contamination and ice on the detector. Here is, again, another piece of copper, also at 20 kV, and there's a thing called amp time, or T time, or something like that. Basically, whenever you give your detector an X-ray, you also give it a certain amount of time to take that measurement. The quicker you make your detector work, the more X-rays it counts, so your dead time is lower. But because it's got to count those X-rays quickly, there's more error in the measurement, so the peaks are wider. And by changing the processor time, or the amp time, or whatever they choose to call it, you can choose to either process X-rays quickly for high peaks that are a bit wider, or process X-rays slowly, which will have a higher dead time, therefore lower peaks, but narrower peaks because you measure the X-ray energy better. And this is copper measured at 20 kV. I adjusted the spot size, so both of them have 25% dead time, and I have in black, I have a quick amp time, and in red, the solid graph, I have a slow amp time. One is for throughput, one is for spectral resolution. You can look at the copper K alpha, and all you really see is a change in height, no significant things. But let's look at the copper L alphas. If I zoom in on the L alpha region, you can actually see there's two little copper peaks there. The L alpha is composed of multiple peaks. When I do slow analysis, long amp time, long processor time, I actually begin to distinguish these weak X-ray energies. I can also see in red a better carbon peak and a better oxygen peak. Really, the carbon's contamination and the oxygen is surface oxidation, but I can pick it up better. Why? Because the peaks aren't smeared out as much. So my advice to you is, if you don't know what you're doing, I usually leave the processor time somewhere in the middle. They tend to go from, say, 1 to 6. So I use, 3 or 4 in the middle. That's a good does everything processor time. However, if I want to map, I go a fast processor time, and if I want to do light elements, I do a low processor time. It's an easy thing to change, just change it. The only thing I ask you is, when you're finished, set it back to where you found it so you don't cause confusion to the next person who never thinks of checking it. The staff can happily show you how to do that. A good example of the Dwayne Hunt limit. This was done at 10 kV, yet if you look at my continuum background, it stops at somewhere about 7.5 kV, 7.5 to 8 kV. So that shows me I had over 2,000 volts of subsurface charging. So that's a good example of the Dwayne Hunt limit. The continuum stops there. This specimen was charging up badly. I can certainly qualitatively say I got carbon, oxygen, aluminium and gold there. Quantitatively, I'll be hesitant to accept the results, the numbers. Having said that, the gold is a gold coating anyway to make the specimen conductive, so there's a lot of problems quantifying that spectrum anyway. I tend to carbon coat to quantify, and I never quantify carbon. Mapping, it's no good for light elements, it's no good for trace amounts and all this. That's what I say. Generally, as most of the advice I'm here is giving general advice for the average person to move forward. Like anything, there's exceptions. Here's one of the exceptions. This is a WDS map I did myself. It's what I call a thermal colour map. A cold colour, like black or blue, means not much, and a hot colour, like red or white, means a lot of it. Top left, chromium. Top right, boron. Bottom left, iron. Bottom right, carbon. You can see I'm picking up subtle changes in carbon, and I can see all the borides. This is a high alloy steel. And there's actually a lot of subtlety to that map and changes I can pick up. It's a good quality map. It did use a WDS detector, which is better at light elements. And that map took me 48 hours to map, 2 solid days. 24 hours mapping on the peak, followed by another 24 hours mapping off the peak. You've got to do that separately with WDS to do a peak above background subtraction. But it produced an excellent map of my light elements in my high alloy steels. It can be done, it takes time. And with that, I'd like to thank my colleagues who helped me out: Eunice Grinnan, Gemma Grayson, Graham Octoloni, Lachlan Casey, Jin Zhao. An excellent reference book is the book referred to as SEM and X-ray Microanalysis by Goldstein et al. It's a very good reference book. I recommend it to you. Thank you so much for listening to me. I appreciate it.